Hello students, today in our electrostatics lesson we are going to see some important questions. They are capacitance for a parallel plate capacitor, then energy stored in parallel plate capacitor. Third one, effects of a dielectric placed in a parallel plate capacitor. Let's move to the expression for a capacitance for a parallel plate capacitor. Now consider a capacitor with two parallel plates. See, a capacitor with the two parallel plates, each of cross-sectional area A. Both the plates have a cross-sectional area A and they are separated by a distance D. Both of them are separated by a distance D. You can see all these things in the picture. Now, the electric field between the finite parallel plates, this finite parallel plates is E is equal to sigma by epsilon naught, where sigma is the surface charge density on the plates and sigma is equal to Q by A. That means the charge divided by the area, cross sectional area. If the separation distance between them are D is very much smaller than the size of the plate, that means the size of the plate is very much high but the distance is very low, then we can put D square is very much less than A, that means the area. The electric field between the plate is E is equal to Q by A epsilon naught. Okay, this E is equal to Q by A epsilon naught. This is going to be the equation number 1. The electric potential between the plates having a separation D is given by V is equal to ED equal to QD epsilon naught. Actually, not many things. We add a distance D here. So, the QD divided by A epsilon naught. This is the second equation. Since the electric field is uniform, the capacitance of the capacitor is given by C is equal to Q by V. That we all know already, because Q is equal to CV. So, we take the V here, Q by V, and instead of V we put the term QD divided by A epsilon 0 using the last equation 2. While you cancel this Q and Q, okay, you get A epsilon 0 in the upper side and the D in the bottom. So epsilon naught A divided by D. From equation 3, it is evident that the capacitance is directly proportional to the area of cross section, okay, and is inversely proportional to the distance between the plates, that means that D. Using this, we understood that the area of cross section of the capacitor plate is increased, more charges can be distributed for the same potential difference. As a result, the capacitance is increased. Now, if the distance D between the plate is reduced, that means it has been shrunk, the potential difference between the plate V is equal to ED decreases with the E at constant. Suppose the distance is increased, the capacitor voltage increases and that becomes a greater than the battery voltage. Then the charges flow from the capacitor plate to battery till both voltage becomes equal. These are the important things in the capacitance for a parallel plate capacitor. Now, expression for energy stored in the parallel plate capacitor. Students, capacitors not only stores the charge but also it stores the energy. When a battery is connected to the capacitor, electrons of a total charge minus QE are transferred from one plate to the other plate. Imagine there is a parallel plate in this question also. To transfer the charge, work has to be done by the battery. This work done is stored as a electrostatic potential energy in the capacitor. Now, to transfer an infinitesimal charge dq for a potential difference V, the work done is given by dW is equal to V dq. Already we know V is equal to Q by C, is it? So, the work done to charge a capacitor is W is equal to, we are taking integral on this, okay, integral on this, therefore from 0 to Q, QC divided by dQ. If you integral this dQ, then you will get another Q. So, Q square by 2C, because this starts from 0 to Q. This work done is stored as a electrostatic potential energy UE in the capacitor. And UE is equal to Q square by 2C or 1 by 2 into CV square, because Q is equal to C into V. Where Q is equal to CV is used, the stored energy is thus directly proportional to the capacitance of the capacitor and the square of the voltage between the plates of the capacitor. The effect of a dielectric which are placed in a parallel plate capacitor. The dielectric can be inserted into the plates in two different ways. First one, when the capacitor is disconnected from the battery. Let us consider a capacitor with two parallel plates, each of cross-sectional area A and R, separated by a distance D. As usual, we saw in the first question. Now, the capacitor is charged by a battery of voltage V0 and the charge stored here inside the capacitor is Q0. The capacitance of the capacitor without the dielectric is C0 is equal to Q0 by V0. Let us consider this as a equation number 1. The battery is then disconnected from the capacitor and the dielectric is inserted between the plates. As you know, in the last class we saw a lot of things about the dielectrics. The dielectrics does not allow any charges to flow from left to right or right to left. The introduction of dielectric between the plate will decrease the electric field, and experimentally it is found that the modified electric field is given by E is equal to E0 divided by epsilon R. Students, you can see here there are two parallel plates. Okay, they have been connected with the charge, that means the battery, and here E0 is the electric field inside the capacitors. One is plus and another one is minus charged, and they have been separated by a distance D. Here in the second picture you can see the battery is disconnected, so here you cannot see the electric field here in between the capacitor. Okay, but the distance is same. There is no difference in the distance. Okay. E0 is the electric field inside the capacitor and ER is the relative permeability of the dielectric, or simply known as a dielectric constant. As you know, dielectrics, they does not allow any electric fields to move. The charges cannot move in between the dielectrics, and ER is greater than 1. The electric field is E is less than E0. E0 means the electric field. Now, as a result of the electrostatic potential difference between the plates, V is equal to ED is also reduced. That means the potential difference between the parallel plates also reduced. But at the same time, the charge Q0 will remain constant. The charges always remain constant once the battery is disconnected. Hence, the new potential difference after the disconnection from the battery, V is equal to ED is equal to E0 divided by ER into D. Okay, and we can put, instead of this E0 D, we can put V0. E0 into D, we can put V0 using this. Then we know that capacitance is inversely proportional to the potential difference. Therefore, if V increases, the potential difference increases, the capacitance also decreases. But in reverse, if V decreases, the C increases. Thus, new capacitance in the presence of dielectric is C is equal to Q naught by V. C is equal to Q naught by V, which is, you can put this ER and V naught, Q naught divided by ER into V naught, this term. Okay, we are replacing V here. If you replace the V, then you have to put V naught by epsilon R. Now epsilon R into C naught, because you can take this Q naught by V naught as C naught. So epsilon R into C naught. Already we know if epsilon R is greater than 1, we have C which is greater than C naught. Thus, insertion of the dielectric constant epsilon R increases the capacitance. If you insert a dielectric here, then it increases the capacitance of the capacitor. You understand? Again, using that equation, C is equal to Q by V, you can put, instead of V, you can put QD by A epsilon naught A by D, while cancelling the Q. Okay, C is equal to epsilon naught A by D. C is equal to epsilon naught A by D. And we can term this epsilon naught R and epsilon naught A divided by D. Instead of epsilon R and epsilon naught, you can have epsilon. So C is equal to epsilon A by D. Where epsilon and epsilon R is the permittivity of the dielectric medium, the energy stored in the capacitor before the insertion of the dielectric is given by U naught is equal to 1 by 2 into Q naught square divided by C naught square. This is the equation number 6. And after the dielectric is inserted, the charge Q naught remains constant, but the capacitance is increased. As a result, the stored energy is decreased. Therefore, U is equal to 1 by 2 Q naught square divided by C is equal to 1 by 2 Q naught square divided by epsilon r into C naught. We change this C as epsilon r into C naught. Okay, and we can replace this term u naught. We can replace this term u naught, which is equal to 1 by 2 q naught square divided by C naught here for these terms, except the epsilon r. So u naught divided by epsilon r. Since epsilon r is greater than 1, we get u which is less than u naught. That means here the u is referred as the potential energy. There is a decrease in energy because when the dielectric is inserted, the capacitor spends some energy in pulling the dielectric inside. That's why there is a decrease in energy while we insert a dielectric there. Therefore, when the capacitor is disconnected from the battery in this section, there is a decrease in energy. That's the final information. Now, let's see what's happened when the battery remains connected to the capacitor. Let's now consider what happens when the battery of voltage V0 remains connected to the capacitor when the dielectric is inserted into the capacitor. The potential difference V0 across the plate remain constant. That's an important thing. Then when a dielectric is inserted, the charge stored in the capacitor is increased by a factor of epsilon r. Therefore, Q is equal to epsilon r into Q naught, because here the epsilon r is the increased charge. Then due to this increased charge, the capacitance is also increased. If the charge is increased, the capacitance is also increased. Therefore, the new capacitance become C is equal to Q by V naught, or epsilon r into Q by V naught, because we have to replace the Q here. Okay, we have to replace the Q by epsilon r into Q naught, and we know Q by, instead of Q by V naught, Q naught by V naught, we can put C naught here. When the battery remains connected is different from the case when the battery is disconnected before introducing the dielectric. In the earlier case, we saw the battery is disconnected before introducing the dielectric. Now, C naught is equal to epsilon naught A divided by D. C naught is equal to epsilon naught A divided by D from the earlier expressions. And if C is equal to epsilon A by D, the energy stored in the capacitor before the insertion of dielectric is given by, that means we are going to insert the dielectric and we are going to measure the energy. Therefore, U naught, that means the stored energy, is equal to 1 by 2 C naught into V naught square. All these informations we know here. We have not used the expression U naught is equal to 1 by 2 Q naught square divided by C naught square. That means expression for dielectric which shows us the energy stored in the capacitor. We have not used this because here both the charge and the capacitance are changed. Okay, both the charge has been changed and the capacitance also changed. Charge has been changed from Q to epsilon r Q naught, and the capacitance also changed from C to C naught. Whereas in the above equation, V naught only remains constant. After the dielectric is inserted, the capacitance is increased. Hence, the stored energy is also increased. Therefore, U is equal to 1 by 2 C into V naught square, which is equal to 1 by 2 epsilon r C naught and V naught square. Or you can, instead of this terms, from the above equation you can put epsilon r is equal to u naught. Now since we know epsilon r is greater than 1 and u is greater than u naught, then the energy density is given by u is equal to 1 by 2 epsilon into E naught square, where epsilon is the permittivity of a given dielectric material. Thank you students, thank you for your presence. Let's see in the next class.